Good day everyone, this is the introduction to Delta-Wye transformer connection. Part 1, Draw and Observe Delta-Wye connection. So this video is the very first part of the series for the Delta-Wye transformer connection. So in this series, we are going to focus on the delta connection. So to begin, let's first draw a single phase transformer with two windings. So what we have here on the left side is the primary side or the higher voltage side or the source side. And on the right is the secondary side or the low voltage side or the load side. This is the primary side. And this is the secondary side. So we will draw polarity marks to indicate the polarity side of the winding. So this is the polarity marks. And we are also going to draw two parallel lines to indicate magnitude coupling. And lastly, we will assume that the primary line-to-line voltage is 4160 volts and the secondary line-to-line voltage is 480 volts. So what we have here so far is a single phase transformer. And we will put a capital A on the primary side of the winding and a lowercase a in the secondary side winding. So to create a three-phase transformer, we will simply add two other windings. So winding B and winding C. B and C. So now we have created a three-phase transformer. Since we were illustrating a Delta-Wye transformer connection, let's start by connecting our secondary windings in Y. So we are going to connect winding A, winding B, and winding C together. So this is Y grounded transformer connection. So the Y grounded transformer connection has a different characteristic than the Y ungrounded transformer connection. So which will be discussed in a different video. So now we're going to connect the primary windings in Delta. In Delta, a transformer can be connected in a variety of ways, and each connection has its own special qualities. So we are going to explore it on later videos. For now, we are going to draw the most common delta connection, which is called the Delta AB or DY1. So we are going to now connect the primary side. And now we have a Delta-Wye grounded three-phase transformer connection. So this is a Delta-Wye grounded three-phase transformer connection. So that's it for today's video, and thank you for watching. Good day everyone, this is the introduction to Delta-Wye transformer connection. In part 1, we have illustrated a very common connected Delta-Wye transformer connection. So in part 2, we'll look at the relationship between line-to-line voltage and phase voltage for Delta and Y connection. So to start, we all understand that the phase voltage are voltage measured across transformer windings. So first, let's illustrate primary phase A voltage, which is measured across the polarity side of winding A. So this is the polarity side of winding A and the non-polarity side of winding A. And similarly, we'll illustrate primary phase B. This is the primary phase B voltage and primary phase C voltage. On the secondary side, we'll illustrate secondary phase A voltage and phase B and phase C voltage. So line-to-line voltage are measured across two lines. So the most common line-to-line voltage are measured across line A to B. This is line A to B. So line-to-line voltage AB and line B to C. So line-to-line voltage B and C, and line-to-line voltage C to A. So line-to-line voltage C to A. And while on the primary side, where our transformer is connected in delta, we should expect the line-to-line voltage across line and B, line A and line B to equal to the phase A voltage. And similarly, the line-to-line voltage across line B and line C is equal to phase B voltage. And similarly, C and A is equal to phase C voltage. So for a delta connected transformer, we should expect that line-to-line voltage is equal to phase voltage. Line-to-line phase voltage. So next, on the secondary side where our transformer is connected in Y, we'll have a different relationship between line-to-line voltage and phase voltage. So we have a different relationship between this and the phase voltage. We will discuss it in a new video. So line-to-line voltage measured across the line A and line B is equal to phase A voltage is equal to phase A voltage minus phase B voltage. So for a Y-connected transformer, if we look at the magnitude alone, we should expect the line-to-line voltage to equal to square root of 3 times the phase voltage. So for line B and line C, we have is equal to phase B voltage minus phase C voltage, which is also equal to square root of 3 times the magnitude of phase B voltage, which is also equal to square root of 3 times the magnitude of phase C voltage. Next. So as of the primary side, if we measure across line and line B of our transformer using a voltmeter, we should expect 4160 volts. This is our line-to-line voltage we assumed in part 1. This 4160. And since the primary side of our transformer is connected in delta, we should expect that the line-to-line voltage is equal to our phase voltage. So our phase voltage would have 4160 volts. And so similarly, the voltage across line B and line C is also 4160 volts here. So voltage phase voltage B will also have 4160 volts and phase C voltage. As I said earlier, for delta connected transformer, line to line voltage is equal to the phase voltage. So for delta connected transformer, line to line voltage is always equal to phase voltage. While on the secondary side, where our transformer is connected in Y, if we measure the voltage across line A and line B, we should expect 480 volts from line to line voltage. Again, this is the voltage we assume in part 1, 480 volts. And so what voltage should we expect if we measured across the polarity side of winding A, polarity side, and then polarity side of winding A? Well, we have to derive that from line to line voltage. So remember the relationship? For Y connected transformer, the line to line voltage across line A and line B, line to line voltage of A and B is equal to phase A voltage minus phase V voltage, which is also equal to square root of 3 times any phase voltage. So let's calculate. We already have our line to line volts, so we have 480 volts equals the square root of 3 times phase voltage. So let's try and calculate it. So 480 equals to square root of 480 is equals to the square root of 3 sub x. So shift solve. So we have our phase voltage is equals to 277 volts. So our phase voltage is equals to 277 volts. Similarly to our phase voltage V, we also have 277 volts, and also our C. So that's all for the video. So now we know that the relationship of voltage, line to line voltage and phase voltage for Delta-Wye transformer connection. So that's all. Introduction to Delta-Wye transformer connection, Part 3, Current Quantities. In Part 2 of the series, we illustrated the relationship between line-to-line voltage. So in Part 3, we'll cover the relationship between line current and phase current from the Delta-Wye transformer connection. So let's start where we left off. We all know that our secondary side of the transformer is connected in Y with a neutral ground. We understand that the line current or line-to-line current is a current that flows through lines of a conductor. Since we assume that the second side is our side, we understand the line currents will flow through our line to our load. So line-to-line current A will flow through the line A. Here. And line-to-line current B will flow to line B. And line-to-line current C will flow to line C. And they will all feed up our load. So while on our primary side or the source side, which is connected in delta, this is where our source current will come from. So line-to-line current A will flow to line A here. And line-to-line current B will flow to our line B. And line-to-line C current will flow to our line C. So remember this, line-to-line current comes from the source. This is like a generator, a utility, or a grid. So now let's talk about phase current. We understand that phase current flows through transformer windings. So let's start on the secondary side where our transformer is connected in Y. So we should expect A current to come from winding A and flow to our load. So it's come. And similarly to our phase B and C current. Phase current C. For a Y connected transformer, we should expect phase A current and line to line current to be the same. So line to line, phase A current is equals to line to line current A. Now let's start the primary winding. So since the current flowed through transformer windings, the delta transformer connection is no exception. Let's begin with winding A. Since we know that the secondary phase A current here flows out of the dot, so the primary A current, phase A current will flow into the dot here. It flow into the dot. So this makes sense, right? We will simply following the dot convention. We were simply following the dot convention. If current goes into the dot from one side, then the current must flow out of the dot on the other side. Here, it flows out, and while in the primary, it goes in. So that means phase A current and phase B current flow into the dot on the primary side. So A and B will flow into the dot. Here. And so that's how we describe phase current and the line current for Delta-Wye transformer connection. And thank you for watching. Introduction to Delta-Wye transformer connection, Part 4, Current Relationship. In Part 3, we introduce line current for the Delta-Wye transformer connection. In Part 4, we will explore the relationship between line current and phase current for Delta-Wye connected transformer. So, we understand from Part 3, primary phase A, B, and C flow through the polarity side of the primary windings. Here, polarity side. And the secondary phase A, B, and C currents flow out of the secondary windings. Here, it flows out. For Y-connected transformer, it's very easy to see that phase current and line current are both equal. The line-to-line current and the phase current are both equal here, this and this. However, for delta-connected transformer, we don't have the same one-to-one relationship between line currents and phase currents. So, let's label a few things to be very clear and concise. We will call node A1 the node that connects the polarity side, here, the yellow, of winding A and the non-polarity side of winding C, here. We will call the node B1 the node that connects the polarity side of winding B and the non-polarity side of winding A. And lastly, we will call node C1 the node that connects the polarity side of winding C, here the green, and the non-polarity side of winding B, here, blue. So, we know from part 3 that the primary phase A current flow into the polarity side of winding A and out of the non-polarity side of winding A. Here. which means that the current that flows out of node 1 by definition is phase A current. Yeah. And since that non-polarity side of winding A is connected to primary side of winding B, the current that goes into node B1 is the same phase A current here. Since we define phase A current as a current that flows into polarity side of winding A and out of the non-polarity side of winding A, the current that comes out of node 1 here and the current that goes into node B1 is the same primary phase A current. All the same. Here, here, and here. Now we move to phase B current. So we know from part 3 that primary phase B current must flow into the polarity side of winding B. Yeah. And out of the non-polarity side of winding B. Which means that the current that flows out of node B1 by definition is phase B current. Here. Phase B current. And since the non-polarity side of winding B is connected to polarity side of winding C, the current that goes into node C1 is the same phase B current here. Lastly, let's move to phase C sequence. We know from part 3 again, the phase current must flow into the polarity side of winding C here, and out of the non-polarity side of winding C. Which means that the current that comes out of node C1 by definition is phase C current here. Phase C current. And since the non-polarity side of winding C is connected to the polarity side of winding A here, that current that goes into node A1 is the same phase C current here. It's the same. Okay, so now that we illustrated phase current, let's quickly label our line current from part 3. We know that line-to-line current A will flow through line A into the bushing of winding and finally into node 1 here. Line-to-line current A and here. And similarly with line B and line C. So let's put LLC. Okay, so we know exactly what's going into each node and what is coming out of each node. So we are now going to use the Kirchhoff's law. The law on each node. So we're going to use Kirchhoff's law on each node to describe the relationship between line current and phase current. So let's start from node 1. We can verify that line current A flows into node 1 here. It flows into node 1. And the phase current C also flows into node A1. However, phase current A flows out of node A1 here. So when we apply Kirchhoff's law, we can express this relationship as line-to-line current A plus phase current C is equals to phase current B. I mean A. Phase current A. Similarly, for node B1, line current B here, line current B line current B plus phase current A, phase current A is equal to phase current B here. Phase current B. Similarly with node C1, line C current plus phase current B is equal to phase C current here. And that's it. So that's how we describe the relationship between line currents and phase current for delta transformer connection. And thank you for watching.